also here the title, Algebraic Topology Applied in Geometry, and there are surveys on the topic by Anders Björner in the Handbook of Combinatorics, which is more on combinatorial side than geometric side of such applications, and several surveys by Zhivalyevich, User's Guide to Equivariant Topology, and there is a recent book by Matoušek, which contains much more than I can talk about here. So this is the title, and I will talk about. This is not an outline, but something of an outline. I will touch upon history of the problems. I will give examples of how people use topology, algebraic topology in geometry. I will explain methods, some methods, and some problems as well. And this title could have been Equivariant Algebraic Topology Applied in Geometry, because it's going to be mainly about equivariant algebraic topology, with few exceptions. I try to skip combinatorial applications, because this is geometry. We talk about geometry. Yeah. It's not quite possible. For instance, Lovász's breakthrough result when he showed that Knese's conjecture is correct, gave an impetus to using algebraic topology all over the place, not only in combinatorics but in geometry as well. And there are apologies are the most important thing. I won't talk about a few applications and people and results that would deserve talking about them, but lack of time or whatever. So for some reasons I won't be. So first application is not equivariant topology, and this is probably the first. So this is Hell's theorem, which is known to all of you, which says that if F is a family of convex compact sets in d-dimensional space, and every d plus 1 or fewer of them have a point in common, then all of them have a point in common. This is a famous theorem. He proved in 1912, I think, but published it only 11 years later because of the First World War. And when he published it, several proofs appeared by other people. Still, it's his theorem. There was no question about that. But he worked on the topological version of this theorem, and he proved the following topological version. This time, the sets need not be convex. They're just compact sets. And instead of having non-empty intersection for every d plus 1, you insist on having contractible intersection for every d plus 1 or fewer. Then the condition holds again. All of them have a point in common. This is a simpler theorem by now because of the Nerf theorem of Leray. But I mean, the proof is simpler than it was then. But it's still a good theorem. It was recently used in a nice paper by Gil Kalei and Jiří Matoušek. Actually, this version of it, which is a strengthening for the planar case, and I won't read it out loud. I leave it to you to read it. What it says weakens the contractibility condition of Hell's theorem in the planar case. Here I wanted to mention an open problem connected to Hell's theorem. There is a colored version of Hell's theorem, which is due to Lovász, and says the following: F1, F, b plus 1 are families of finite families of convex sets in Rd, with the property that no matter how you pick a convex set from this one, from each one, they intersect. Then the conclusion is that one of the families is intersecting for some I, f sub I is intersecting. So this is a generalization of Halley's theorem, right? Because if you take the same family d plus 1 times, and you take Halley's condition, then the condition what I wrote over here holds. So one family must have a point in common, but all families are the same. So this is a generalization. And I wanted to mention that the topological version of this one is missing. That's an open problem, but I was informed by Gil this morning that it's not missing anymore. He proved it with Borsuk-Ulam very recently. So this is not an open problem anymore. My next topic is Borsuk's theorem, which is indeed the starting point of equivariant topology. And here are several versions of Borsuk's theorem. I'd rather call it Borsuk's theorem than Borsuk-Ulam theorem, because Ulam just posed the question, which is very important as well, but not, I mean, it's Borsuk's theorem. But opinions differ on that. Matoušek calls, the title of Matoušek's book is Using the Borsuk-Ulam Theorem, so he uses both names. And so here are different versions, and the first one is that Sn is, just a moment, everything I'm saying is clear, so I'm talking about intersecting families and Sn and Rn, where Sn is the n-dimensional sphere, Rn is the n-dimensional Euclidean space, etc. If something is unclear, please let me know. So if there is a continuous mapping of Sn onto Rn, you press the sphere onto the plane, then two antipodal points end up in the same position. This is Borsuk's theorem, first form over there. A second form of Borsuk's theorem is that if the mapping is antipodal, meaning that f of x is the same as minus f of minus x, so opposite points, antipodal points are taken to antipodal points down there, then there is a zero of this mapping. The mapping has a root. So this is another form of Borsuk's theorem. Another form is that there is no antipodal mapping from Sn to Sn minus 1. This is probably the most well-known form of the theorem, but all of them are equally useful. Here is one which is not so common. If f is from the ball, solid ball, to its boundary, to an n-1 dimensional sphere, which is antipodal on the, then it cannot be antipodal on the boundary. It cannot be antipodal on delta of Bn. And there is a theorem by Lusztianyk and Sri-Nyiraman which turned out to be equivalent to Borsuk's theorem, and it was proved earlier than Borsuk's theorem, saying that if Sn is covered by n plus 1 closed sets, then one set contains an antipodal pair. An identical formulation is with open sets, all of them open, then the same conclusion holds. And actually, Borsuk independently discovered this version as well, and this is that prompted him to think about what has become known as Borsuk's conjecture later on the diameter of convex bodies. Yes, here is one more form of the theorem, which is slightly stronger than not much stronger than Borsuk's original theorem, saying that an antipodal Sn antipodal map has odd degree. So here I don't say anymore that a mapping is continuous. Every mapping is continuous from now onwards. Pardon me?
What's the degree?
What's the degree of a mapping? Good question. What is it? It's you go to a So you map.
Use this blackboard, there's more light on it.
Yes, but then I have to clean it as well. I can't do that. So the degree of a mapping from Sn to Sn is this. You go to a point here, a point called Z, and look up f to the minus 1 z, the inverse of the you assume that your mapping is linear, or you assume your mapping is differentiable. And then, so here is a point on this is Z, and you look up on Sn, and you look up its inverse image, which are several finite many points over there, and you check whether the small neighborhood of Z goes to a small neighborhood of f of minus 1 z here, this way or the other way around. So this is, you compute the roots of the equation with plus or minus 1 depending on which side I go with. So this is a number which is constant on almost every point of the target space. This is called the degree. If you like this, if you compute S1 to S1, how many times it binds around? What direction? Pardon me?
No, it's a sign sum. It depends on what happens to the orientation.
It's a sign sum, yes. It depends on which way the root goes, this way or that way. So this is the degree. And if you have a mapping Sn to Sn minus 1, which is antipodal, then it's degree 0, because at most points it does not take it simply. So degree 0. So this implies that it cannot be mapped into Sn minus 1 because the degree is odd and not 0. Often the crux of the argument is going to be that the degree should be 0, but it's not 0 of an algebraic of such type of arguments. Yeah. So here is one form from the previous slides implies Brouwer's fixed point theorem, and the proof is simple, and I explain it. So this is when Bn is mapped onto Sn minus 1, with the boundary being antipodal, f antipodal on the boundary. So here is your Bn, and this is your point x, and this is your point g, where it takes it, g of x. If g of x is never equal to x, then you can define this map here, f of x. Right? This is uniquely defined and continuous. And this is antipodal on the boundary. And it maps on the boundary. And according to version 4, it's impossible. So this Borsuk is stronger than Brouwer. This is the only thing I wanted to say with that. I want to explain a simple proof of Borsuk's theorem for this audience, which goes this way, and which was found by several people between 1979 and 1981. I was one of them. And I explain it in the very simple case when n equals 1, but that will tell you basically what the proof in higher dimensions is. So here is my mapping from S. This is S1, and here this is S1, and this is R1, and here I have this is I use form 2. So when Sn is mapped onto Rn antipodally, then it has a 0. This is what I want to show. So this my f comes from here to here. So this point x goes to some point over f of x. And the opposite point here, which is minus x, goes to the opposite point over here, which is minus f of, this is it. And they are opposite, so here is the origin. Right? And I take, so this is my f. And I take another map in here, another circle, another S1, and I take a mapping G from here to down there, which is again antipodal, and this is just a projection, say, a linear mapping. So this takes the origin to the origin, and the point from here to this projection is clear. And then I extend it to a map of the annulus between the artificial S1 and the original S1 linearly. So between this point and this point, here is a point, I map it between the two with the corresponding constants. So I get a, so this is a sort of homotopy, cross 0, 1, and this is a mapping F, which is again antipodal in the previous sense in the x variable, not the t variable, but x variable. Are you with me? What I want to show is that this guy has a 0 on the outer boundary. Capital F has a 0 on the outer boundary. So I look at the set F to the minus 1, 0. F to the minus 1, 0. I assume that my maps are nice, both F and G, which you take for granted this time. And then the inverse image is one-dimensional manifold. So it cycles, as many as you wish, and curves from boundary to boundary. Right? So there are cycles here. There is a cycle here, then there is the same cycle appears on the opposite side. And there are curves from boundary to boundary. Now I know that here, there starts a curve, and here, there starts a curve. I want to show that one curve that ends up on the outer boundary. Right? So if it does not, then the guy that starts here should end up over there. Right? If not, then this is the single boundary to boundary curve, and it starts here, and it should end up here. But this point, so it goes somehow, and this goes somehow, but this point is antipodal to this point, and this point is antipodal to this point. What happens to the midpoint of this curve? It has to be antipodal to itself and identical with itself as well. Right? If I walk the same distance from here and meet in the middle, it has to be antipodal at the same time and the same point at the same time. Impossible. This is the proof.
This is 0. Yeah, but you can't be at the center of the circle.
Right. But what happens if this curve that starts on the bottom, I mean, it makes a loop which touches the inner circle?
The inner circle has no other 0 than these two.
No, but suppose that this curve does a loop that ends at the same. See, maybe they don't.
No, this is a regular map, so it cannot start at the boundary in two directions. It doesn't fork away. So there are some missed parts in this proof, because you have to find a generic enough map here, which takes some work. But this is the essence of you can make it work. You can do for instance a piecewise linear approximation to both G and F. And there you apply, and you understand that the 0 is on the boundary of a cell, and it has to start at just one line segment goes out from there. I don't want to explain the further detail. This is the essence of the proof. So applications of Borsuk. It appears that the first application of Borsuk's theorem, or one of the first, is due to Banach, and it is the ham sandwich theorem. And it must be known to all of you. It says that if you have d probability measures in the d-dimensional space, on the d-dimensional space, and I add nice probability measures, I say absolutely continuous, or something like that, then you can halve all of them with one simple hyperplane. That is, there is a hyperplane H such that mu, in every measure, the positive side of that half plane and the negative side of that the positive side of that hyperplane has the same measure as the other side. The proof of the ham sandwich theorem is really a routine from the Borsuk's theorem. The two-dimensional case is not so. No. Here is a theorem by David Gale from 1961 that C1 and C prime are convex bodies in d-dimensional space, and F is a Lipschitz map from C to C prime, and Lipschitz with this constant k. Then the width of k, width of C is at most k times the width of C prime. This was discovered by Bezikovich for the planar case, where it's just in this instance, the application of Borsuk's theorem can be replaced by the fact that if a real function is positive, continuous function is positive and negative at places, then it's at 0 somewhere, which is quite often the case. You discover something and then for a real function, and once you want to extend it, turns out it depends on Borsuk. No, this is the wrong direction. Here is a nice theorem by Hobby and Rice from 1965. It says that, I won't repeat this word nice, I hope, anymore on the transparency. You have to assume that these measures are not too exotic. Every measure can be approximated by a nice measure. And this many probability measures are there on 0, 1, then you can partition 0, 1 into d plus 1 intervals and choose signs epsilon j plus or minus 1, so that this quantity here, epsilon j times the measure of ij, the sum from j to d plus 1 is always 0 for every single I. Here is a picture how it goes. There are 5 intervals. The odd ones go with plus signs and the even ones go with negative sign. And it means that the measure of these intervals is the same as the measure of these intervals in any one of the 5 measures included. There is an almost trivial proof to this theorem. You put the 0, 1 segment on the moment curve in d dimensions. You get d measures in d space. You can cut it with a single hyperplane, according to Ham sandwich. And the cut is just intervals. And the cutting places, at most d cutting places, because no hyperplane can hit this curve more than d times. So you just get it free of charge. It's a coffee house theorem, not in retrospect, I should say. With the ham sandwich, yeah. There is another proof, which is also very nice, based on a map from SD, the d-dimensional unit sphere, to the partitions of 0, 1 into at most d plus 1 intervals. And you should imagine this. So the point on SD is x1, x2, etc., xd plus 1, with squared sum equals to 1. Are you with me? The point on SD is just a d plus 1 tuple with sum squares equals 1. And then you go to 0, then you go to x1 squared. This is the next point on your interval 0, 1. And then you go to x1 squared plus x2 squared, which is the next point, the end point of the second interval, etc. And you can include the epsilon I in the proof that would come here with the sign of x, sign of the corresponding xj, and look at the function that comes out. And this map was used by Thomas Kaiser in an interesting application of Borsuk in geometry, between geometry and combinatorics. And actually, Gábor Tardos understood that the problem is connected to topology, and a better way was, and more efficient way was this embedding. This is on intervals, multiple intervals. Here is another form of the same theorem, discovered by Goldberg and West, and the better proof was given by Alon and West on these years. An open necklace with d kinds of stones, 0, 1 interval with atomic measures, d atomic measures, and there are two thieves, and they want to split it equally between themselves. And the question, how many cuts are needed to take them apart and reassemble them to get equal amount of this each stone? And the points are needed, and the proof is just a discrete version of the previous proof, or approximation, or whichever you want. What happens in case when you have more thieves? That's a more difficult problem that's solved by Alon in the same year, and it's written over there how many cuts suffice. D times t minus 1, which coincides with when t equals 2 with the truth. That needs more sophisticated tools, and I'll come to that probably later. Here is another piece that we will encounter later often, I mean the setting at least. There are finite sets in d-dimensional space, each of them having n elements, pairwise disjoint, general position if you wish. You can call them colors. And what you want to find is n sets, S1, Sn, each of them of size d, such that each S intersects each color in exactly one point. And here is the picture. The colors go this way. This is not in d-dimensional space, just the combinatorics of the setting. The colors go this way, and the sets Si go like edges in a complete, like in a d-partite graph. And what you want to see, you want to find such an S's so that the convex halves are pairwise disjoint. And so this was proved by Alon and Akiyama, and the proof is, I give you the proof straight away. It's induction by n, and I give the proof for d equals 2, but the same proof works in any dimension. D equals 2n induction. N equals 1 is trivial. You you cannot intersect anything. And then if n is odd, then you use a ham sandwich cut for the red points and the blue points. Then you get a line in the plane, a red point here and a blue point here, and n minus 1 over 2 red and blue points on this side, and n minus 1 over 2 blue points on this side. Now, this is, you match up these two. This is your set S1, and you apply induction hypothesis up there and down there separately. They will not intersect this guy anymore, or the guys below. So this is, and for n even, you figure out what to do. It's the same thing. Here is one more called the center point theorem, which is not quite.
Triviality that we have sandwich cuts by chromatic.
I think so. You have to. So if you make very small circles, and the points are in general position, then you have to have half volume, and there is no other way to have two things than through the center. I didn't go through this argument for a long time. This is true. The center point theorem of Rado says that if you are given a probability measure on RD, then it has a center point. A center point, that is a point, so that no matter how you pick a half space containing that point, that half space has to have large, at least 1 over d plus 1 measure. This you can prove it using Helly's theorem. This was the original proof, or Brouwer's fixed point theorem. Both of them imply it. And here is a very neat generalization, or common generalization of the center point theorem and the ham sandwich theorem, which is due to Zhivalyevich and Rechitsa and independently by Dolnikov. So if you have k probability measures on RD, then there is a k minus dimensional affine flat F with the same property as before. Any half space containing that affine flat has a fixed fraction of each measure, and that fixed fraction is 1 over d minus k plus 1. The proof is not an application of the Borsuk theorem. It is more involved. But I just wanted to show you a nice topological statement. This is end of examples, and the method comes next. But I explain it on this theorem, Radon's theorem. So I covered this part because I don't want you to read it for the time being. Radon's theorem is a very simple thing. You have d plus 2 points in d-dimensional space. Then it splits into two sets. A splits into B and C, such that the convex halves of A and B intersect. This is an elementary statement with a very simple proof. And Radon actually used it in 1922 to prove Helly's theorem. But you can reformulate this statement slightly differently. And for that one, I call delta d plus 1 the d plus 1 simplex, the notation. And Radon's theorem can be stated this way. If you map the d plus 1 simplex onto d-dimensional space, then there will be two disjoint faces whose images intersect, mapped by a linear mapping. So what's going on here, this is your plane, these are your 4 points down there. If you look at the partition, then this is the partition here, they intersect. What you do instead, you lift these points up in high dimensions. So this goes here and this goes here. This is a d plus 1 this is a three-dimensional simplex. And if you map it back, the points become points. The faces become the convex halves of the corresponding points. So the statement that there will be an intersecting partition, convexly intersecting partition, is equivalent to saying that there is a face and an opposite face, and two disjoint faces whose projections intersect. So this is exactly the same theorem. And but what you can do is this: you can ask, what happens if you assume only continuity of this map from the simplex into RD? So if you want to make a drawing of the simplex, or d plus 1 dimensional simplex in D space, then you inevitably meet some intersections, illegal intersections. But what if you want to cheat a little? You just distort the picture. Well, the following theorem tells you that it's impossible. And this is what I proved a long time ago with Erwin Bajmóci. The same is true for any continuous map from the d plus 1 simplex into the D space. Actually, it's enough to assume that the map is defined on the boundary of the simplex because there is no use of the interior. But it's all the same. Now, on this example, I want to explain the method that is used here. So the method goes with what you call phase space and test map and target space, which are just words, but useful words to explain a very natural thing. So what is the phase space? I look at pairs xy from delta d plus 1 cross delta d plus 1. So this is a pair of points from the simplex with the support of x and the support of y disjoint. The support of a point is the minimal phase containing it. So in my previous picture, you know what I'm talking about. Any questions? No. So this is my phase space because I want to find a point in this phase space, which I denote by delta star, that is mapped onto the same point. This is my target. I want to find a point from this space, so that f of x and f of y coincide. So I define a mapping which I call f star from delta star to some space which is f star on a pair, very trivial, is f of x and f of y, this pair. And I want to see this pair, if they coincide or not. So this mapping goes to RD cross RD. The only thing I want to show is that this mapping hits the diagonal. The only thing I want to show that this mapping is the diagonal. Diagonal is the set of pairs Z from RD. If it has this diagonal, then I'm in business, because that's where f star xy equals z, then they are equal, and I'm there. So assume it does not. So assume this map goes to the product minus the diagonal. Right? And I want to show that such a map does not exist. Of course, I can't prove such a thing, because I take a constant map over here, and then there exists something, so I have to use something extra. I need something extra. And the extra is a group action on this space, which is going to be equivalent with this mapping. Z2 acts on delta star and on RD cross RD. So Z2, what does it mean that the group acts on a space? It means that its action is denoted by omega. Omega takes any point of this space onto the point itself, onto that same space. And here as well. And what's going to be that action? So xy of omega is going to be y and x. So this is a very natural symmetry of this space. The same symmetry appears here, because omega of u and v from this product space is equal to v and u. Just exchange the two components. And so this mapping is going to be invariant under this omega. So if I map omega here and omega here, forget about the diagonal for the moment, then this mapping is commute. So if I go f this way and omega down, or if I go first omega and then f, I get the same thing. It's all the same where I change the two components, before or after. So what you can show is that there is no such equivariant map, equivariant with respect to this action. Right? So this is the method. This is called phase space, this is called test map, and this is called the target space. Now the target space is reduced, and you understand immediately how it is reduced. This is an RD here, and this is another RD here, and this is the diagonal, and then you project everything onto the orthogonal complement of the diagonal. That does not change the action of omega, I mean compatible with the action of omega, and then it lies on this RD, complementary RD. But if it avoids the origin, then you can pull it to the circle, to the sphere over there. So this is the same thing as SD minus 1. And same thing with the omega, which is the opposite operation, taking x to minus x, or u to minus u. I do not explain this simple computation here, but this is the same thing. So now what you have is you want to show that let me call this is the target space. So it depends on what you want to call target space. We may call target space in this instance that SD minus 1. So what you have here is there is delta star, there is f, there is SD minus 1, and there is negative 1, SD minus 1, and f goes here, and delta star, and here is omega. And I want to show that such a map which computes does not exist. I jumped over the RD cross RD minus diagonal, left out from this picture. Now, what I want to do is I want to embed SD over here. Embed SD over here with Z2 action again, namely taking the opposite, the antipodal. If I can do that, this is in contradiction with Borsuk's theorem. So this is what I want to do. For that one, I only have to understand that this guy here is d minus 1 connected. Then I can map it into. But there is so that this can be done has a direct proof. And I don't go into that direct proof. I just mentioned to you that delta d plus 1 minus delta d plus 1 is a Minkowski difference here, produces you a symmetric body in which opposite points correspond to pairs x, y from this space. And its boundary is SD. Typically, this is the harder part of the story, to show that this guy is connected enough, and then you can embed the corresponding space. So this is the method. I don't have much time left, but yes, there is some more to this thing here. It works not only for delta d plus 1, the simplex, but for any polytope up there. Antipodal is a pair of points x, y is called antipodal if they have parallel supporting hyperplanes. Distinct parallel. And it's true for any convex body as well, not only polytopes in that wording. And this theorem was discovered by Lovász and Scriver in connection with the Holland-Verdier number for some dimension, for some value. And there they proved that the number of for polytopes, number of pairs whose images hit each other is odd. So that's another form of Borsuk theorem, if you wish, oddity of the degree.
They saw somehow that something is linked with some other thing?
Yes, this is a consequence in 5 dimensions, or I don't. So here is so Radon's theorem tells you how large set can be split into 2 disjoint parts with their convex halves intersecting. Zerber's theorem tells you the same thing when you want to have R parts. And here is the right quantity. So n is R minus 1 times d plus 1, this large number. And F is a mapping from that simplex, n-dimensional simplex, to the d-dimensional space, and is linear. Then there are pair by disjoint faces F1, Fr of delta n, so that their images have a point in common. If you translate it back to points, that is the vertices of delta n plus 1 points they come down into d-dimensional space. That means that if you have n plus 1 points, R minus 1 times d plus 1 points in d-dimensional space, then there is a splitting into R disjoint sets whose convex halves intersect. So, the question is again whether can you replace linear by continuous or not. So this is Tverberg's theorem from '66, and the question is whether you can replace it by continuity. So to say, Tverberg's theorem is not only holds not only because of the linear structure of the space, but the topological structure of the space as well. Same applies to Radon's theorem, of course. And here is a theorem that I proved with Schlossmann and Szűcs a long time ago. Same holds for continuous mapping if R is a prime. No, you don't like it. You like it?
Well, the last hypothesis is the point.
Yeah. So R is prime this has been improved to when R is a prime power by Özaydin in 87, unpublished, Volovikov in 94 for R prime power again, and Sarkaria found another proof in 2000 for the same thing. But this is an open question for other R's. And I tell you the reason. So this is, again, you can apply the same phase space, target space, and test map setting, and there you have another group acting on the corresponding space, and that group is ZR, shift of the R components. Well, what's the phase space here? You take R copies, R points from this set with pairwise disjoint supports. This is your phase space. If you understood what I was talking about for radon, you understand this is what you have to take. The mapping is just f of the first component, second component, etc. You want to show it histodiagonal. So the target space is the product of R d R times, the diagonal taken out. You project it down, you get again a sphere. This is your target space. Of course, there is a mapping from that space to that space, a constant map. But here you have the shift operation keeping it the same. So if you move the first, I think I have talked enough about that. I stop here. So you can continue this. So there is a group acting, and that group is ZR, cyclic group on R, shifting R elements, and that its action is free only for primes. So free means that the orbit of any point has R points, and as soon as R is not a prime, some orbits get shorter, and it does not work. You cannot embed from front, and you cannot continue this mapping either. So simply it collapses. I can't go into the details of this other proof. I started the proof, but here is a crucial lemma in that thing, which is not so easy to prove, namely that delta star, that is the R tuples of that simplex that have pairwise disjoint support. This object is highly connected. This is not easy to prove, and this is, as I mentioned, this is the hard part, that this guy is highly connected, but can be done. And then here is a theorem that I wanted to prove, but I won't have time for it, so I just tell you how it goes. It is due to Krasnoselski and Zabrejko. Krasnoselski had several theorems that into this direction. And in the book, this is proved actually in more generality, that if the ZP acts on SK freely, P need not be a prime here, and omega is its action, and the mapping G is equivariant from SK to SK, which means simply that there is an omega X on SK, and this diagram commutes. So G is an equivariant, omega equivariant map, and its degree is congruent to 1 mod P. So this contains Borsuk for P equals 2, right? Because it tells you that the degree of antipodal map cannot be 0. One form of Borsuk I proposed you. The proof, we have a separate proof in that paper from 1981, which is quite elementary. A little topology is needed, just the concept of a degree, so I don't go into details. And this works without assuming that P is a prime. Here is something I mentioned already. The continuous Tverberg is true for prime or prime powers, but open for other R. There is a better proof of the continuous Tverberg theorem by Sarkaria. Better proof in the sense that what we did here is taking product of the of the simplex with itself r times. And you can do another operation called join. You can take r for join of the space with itself, and there the connectivity becomes simpler. Connectivity comes almost free of charge, not quite, but almost. And that shows also some connections to Van-Kamp and Flores type theorems that prove. There is, this is the theorem that is applied to one necklace and many thieves. And there, miraculously, primality of R does not matter because of a combinatorial fact that you can continue splitting. There is an open question by Kiersma, who offered a big Dutch cheese for solution. And it said that the number of Fairberg partitions on that many capital N plus 1 points is this big, r minus 1 factorial to the d, and we are very far from any proof. Actually, absolutely unclear whether this is true or not. There is no other evidence than the unique example that we know of where you know all Fairberg partitions, right? And this is not too many. But there is a lower bound for an approximation to the conjecture, stating roughly that there are at least r to the d times r half Fairberg partitions. So this is r to the d times r, and the exponent, the square root of that quantity is more or less is proved by Vucic and Zhivalyevich using algebraic topology again. Here is a theorem due to Dold from 1983, which replaces often the application of that lemma degree congruent to 1 mod p. But this is essentially the same thing, but often easier to use. If a group acts on x and y, x is highly connected, and the dimension of y is at most n, and the action of zp on y is free. Each orbit is of length p. Then there is no x to y equivariant map. So this is often easier to use. You don't have to, this is a module, you don't have to do anything, just prove that it is equivariant and connected, etc. It works for other groups as well, other finite groups as well. There is some condition on why it has to be some compact space or something close to it. How much time do I have left? 6 minutes. Then I embark on a new, oh no, not new adventure, Kaller-Tverberg. So Kaller-Tverberg, I formulate it as a question. So you are given set C1 as a CD plus 1 in RD. This is sets in general position, finite sets in general position. Each has exactly T elements. And so this is the setting. And the question is, can you find sets of the following type? And there comes again my previous picture. So this is not the geometric picture as the points lie in the d-dimensional space, but as they lie in combinatorially. So this is the first color class, this is the second color class, this is the third, and this is the last color class, CD plus 1. And so each of them has size T. And what you are looking for is a set S1 heating each color class exactly once. So this joint set, S2 heating each color class exactly once. A third set heating each color class exactly once, etc. You want to find altogether R such sets. This is possible, of course, but there is a strong condition here that the convex halves must intersect. This is just the opposite of the Akiyama-Alon theorem, where they had to be pairwise disjoint. Here they all have to have a point in common. And so Can you do that? Can you do that if t is chosen very, very large? It's your power to choose it as big as you wish. So this question came up in connection with halving sets in higher dimensions, and even in 3 dimensions. And the answer is that, so this is the question. Is the question clear? Yeah?
Say intersecting exactly 1 or
Exactly 1 point. So, yeah, exactly 1 point. Sometimes 1 point is maybe superfluous, but I don't mind. Here are 2 simpler results that this function t, r, and 2, that is in 2 dimensions, 3 colors, you need r points in each class. Then you can make up r triangles, multicolor triangles, pairwise disjoint vertices that go through a fixed point. This, the proof is topological in the sense that it is done by moving the points one by one, a method that has been explained here before. And there is a proof that T of D, 2 and D, you want only 2 such sets, needs only 2 points in each class by Lovász, and this is a direct use, a beautiful use of Borsuk's theorem. And this was open for a while, and Zhivalyevich and Rečica proved it in '92, that this TRD that I defined previously is finite. And actually, if R is a prime, then it's smaller than 2r minus 1, not so big at all. And primality again comes because of the group action is bad otherwise. But if this is so, then for every r, you have a good bound on this function t. Now, by now there are several proofs of this thing. The crux is again to prove that the phase space is connected enough. And the phase space is essentially a positions of rook positions on a chessboard that don't hit each other. This is the complex. And you want to see n by m chessboard, and you place rooks so that no 2 of them hit each other. This defines a simplicial complex, and the question is, what is its connectivity? There are several topological proofs, but I can't go into any one of those. Here is the statement. So here P is a prime, and these are pairwise disjoint color classes, each of size 2p minus 1. And the simplicial complex is defined as follows. The vertex set is just the union of the colors, the sets of colors. And the simplex, which I call S here, is sigma over there, is a set that hits each color class exactly 1 point. Abstract simplicial complex. And what you want, the phase space is the direct product of these guys, R times or P times, or P times. And you want to show that if you map it onto the corresponding space, etc. Turns out the direct product is not connected enough. Absolutely not connected enough. Very far from being connected enough for this proof. So here comes deleted joins. If you use deleted joins, then you end up with this rook position complex for the deleted join of this space, and you come up with the Zhivalyevich-Rečica theorem, which goes also under the name of topological, the Color-Tverberg or topological Color-Tverberg, which is written over there. So this theorem has several consequences in convex geometry. Not only the number of halving planes, but some others as well. I consider it a victory for algebraic methods, because there is no linear proof. There is no geometric proof of the linear version of this theorem. So there are simplices in 3 space and points in 3 space, 4 colored. You want to find simplices, pairwise disjoint simplices that intersect, only 4 of them, not too many. And there is absolutely no linear proof of that. I wanted to talk about something else as well, but I don't have time for it, so I stop here. Thank you. Yes?
For the continuous algebra theorem, how does Sarkaria say go from prime to prime power? I mean, what's involved in that step?
I don't quite know. It is. I don't know. It's.
I mean, how does it get around the fact that if you z p to the d has subgroups, I'd say?
I never checked the proof. I don't know. Next question.
I was just wondering, in connection with that, I would have thought that probably the fields with p to the k elements were coming up at all n longest to the way that the
I can't hear what you say.
prime field goes. I was just conjecturing that the fields with p to the k elements, the polynomial fields, would play the same role that the number fields, the integers mod p, are playing in the prime case, but I don't see how to do. I mean, it feels like that should be what's involved, but I cannot picture how those polynomials are going to, over the prime field, are going to. I don't see how that.
Yeah.
What about for particular small values of arbitrary the prime or prime power, like r equals 6?
Not known.
Not
Not known either. No. Yeah.
Is there a combinatorial proof for the two thieves theorem? Just a purely combinatorial proof?
Well, yes. There is a purely combinatorial proof of. So you can put it together from purely combinatorial proofs of the Borsuk theorem, for instance. And Matuszek has a purely combinatorial proof of Borsuk's theorem. Of Kneser's theorem and of the Kneser-Lovász theorem, and which avoids using Borsuk-Ulam. And you can, but this is essentially doing topology, not using words of topology. And Günther Ziegler has a similar proof for this p-adic version or ZP actions. Which is again an interesting thing that you can prove things without using topology directly, but in a sense it's topology. But I don't know a direct straight proof of the theorem.